One of the main factors influencing the local earthquake shaking characteristics is the velocity structure of the shallow subsurface. Hereby, the geology has a large effect on the ground motion. For example, soft sediments amplify the ground motion, and therefore buildings in these areas are more prone to earthquake damage compared to constructions on firm bedrock, as is illustrated by this figure here. Because of that, it's important to understand the 1D velocity structure underneath buildings. So how can the velocity structure be estimated? The most common methods in the field of microzonation are array measurements, which require several stations. The wave field arrives at the different stations at different points in time, and therefore the velocity and the direction of the wave field can be estimated. This method gives us reliable results, however, the installation and maintenance is very complex. So the question is, can this also be done with a single station approach? Such single station approaches already exist, such as the horizontal to vertical spectral ratio method. However, they only give us ambiguous results. So in this paper, we introduced a new method of 6 component measurements, which includes 3 translational and 3 rotational motions. This is a single station approach, which in our case requires 2 instruments. First, a trillium compact seismometer for recording the translational motion, and second, the Blue Size 3A rotational motion sensor for recording the rotations. The 2 instruments have to be placed very close to each other in order to record the same movement. As an input signal, we use ambient noise in a frequency range of 1 to 20 Hz, which corresponds to urban noise. And such a measurement lasts about 2 hours. Our study area is Munich's inner city because here a new large geothermal project gives rise to induced seismicity, and therefore it is important to understand the ground motion in this area. Employing the relation between translational and rotational motions, the phase velocities of LoF and Rayleigh waves can be estimated from the 6 component data. Those dispersion curves are then inverted to obtain the local P and S wave velocity profiles. The inversion gives us a range of possible velocity profiles, where the most likely ones are shown here in yellow. The great thing is that in Munich we have borehole-derived lithology, which allows us the direct comparison between the velocity profiles and the lithology in this area. And as we can see in this figure, there's a good positive correlation. The velocity jumps coincide with the groundwater table as well as with the change in lithology. Our results show that this new approach is a great alternative compared to existing methods. It can be especially used in situations where an array setup is difficult, for example in inner cities, volcanoes, oceans, or even in planets. Okay.